In this video, we are going to explain you the fundamental theorem of vector space homomorphism. So we take two vectors v and u be the vector space over the field f, and u be an f from v to u. We are taking a linear transformation or a vector space homomorphism, which is done onto vector space homomorphism with kernel k. Then we have to show v by k is isomorphic to u. So first of all, we have to show that v by k is a vector space. So for v by k to be a vector space, k should be a subspace of v. So k is kernel f. So we have shown already in the previous video that kernel f is a subspace. So here we have to proceed in the same way, and we'll get that kernel f is a subspace of v. So we have shown. After that, we have to define a mapping. So we have to define a mapping psi from v by k to u. Okay, so we have to define this mapping. So we have, suppose we take v by k here, v by k to u. Then we can always have a onto mapping from here. So v by k is what? V. Okay, so this to v, and from v we already have a mapping f, which is onto. We already have a mapping f from v to u. We already have a mapping f. So this mapping I donate by eta, and this is your psi. So psi is nothing but psi applied on v plus k is same as f composite on eta applied on v plus k. Okay, so f eta v plus k is same, we get here f of eta v plus k is v, because this is the definition of eta v plus k is sent to v. Okay, so we got f of v. Okay, so we'll try to define psi of v plus k as equal to f of v, where v belongs to v. Now we have to show that this mapping psi is well defined. We have to show that this psi is well defined. To show psi is well defined, we'll take two elements in the domain set. Okay, so I'm taking two elements which are equal. Then I have to show that the image is also equal. So I take two elements in the domain. So this is for well defined. You take two elements from the domain. So v1 plus k is one element, and another element I take as v2 plus k. So these two should be equal. Okay, these two should be equal. Then you must bring this one this side. So we get here v1 minus v2 plus k equal to k. So you have done in your group theory that a plus h is equal to a plus h is equal to h. Then this implies if and only if a belongs to h. We have done this. Or in multiplication, you have learned in group 3 that ah is equal to h. Then this if and only if a belongs to h. So I'm using that property. Using this property here, I can say that this belongs to k. So here we have v1 minus v2 belongs to k, and this k is nothing but kernel of f. So anything belongs to kernel of f means f of this should be 0. So f of v1 minus v2 is equal to 0. Now this we got here, since f is a linear transformation. Okay, since f is a linear transformation, we can write f of v1 minus f of v2 is equal to 0. So this implies f of v1 equal to f of v2. So by using the definition, what we have defined, f of v is equal to psi of v plus k. So this will be psi of v1 plus k, and here we'll get as psi of v2 plus k. So we took two elements in which are equal, then we got the image is also equal. So this shows that psi is well defined. So we have here psi is well defined. So we got that psi is already well defined. Now we'll try to show that psi is a vector space homomorphism. So we'll take psi v1 plus k plus v2 plus k. I took two elements, so this defined according to the definition of adding two elements in v by k is given by v1 plus v2 plus k. So by definition of psi, this can be written as f of v1 plus v2. So since f is a linear transformation, is a vector space homomorphism, since f is a vector space homomorphism, okay, since f is a vector space homomorphism, this can be written as f of v1 plus f of v2. Okay, we can write this f of v1 plus f of v2. Now f of v2, by definition of this, definition of psi, this is nothing but psi v1 plus k. Okay, plus psi v2 plus k. So, and next we have to show psi of alpha applied on v1 plus k is equal to, where alpha belongs to the field. So we have psi alpha v1 plus k. So this is equal to, by definition of psi, we have this is nothing but f alpha v1. Since f is a linear transformation, this can be written as alpha f v1. Okay, alpha f v1. So by definition of psi, this is psi v1 plus k. So we get here psi v1 plus k. So we have the proof, the both conditions. So this shows that psi is a vector space homomorphism or linear transformation. The vector space homomorphism. So we have shown psi is a vector space homomorphism. Okay. Now next is we try to show psi is 1, 1. So I'll take two elements, psi of v1 plus k is equal to psi v2 plus k. So by definition of psi, this is f of v1, which is equal to f of v2. Now this can be written as f of v1 minus f of v2, which is equal to 0. Since f is a linear transformation, this can be written as f of v1 minus v2, which is equal to 0. So since f of v1 minus v2 equal to 0, that means this element belongs to kernel f. So we have v1 minus v2 belongs to kernel of f, which is equal to k. So this, by using this condition here, okay, this is if and only if. So this can be written by using this condition here. This can be written as v1 minus v2 plus k is equal to k. So this implies v1, bring this one to this side, so v1 plus k equal to v2 plus k. So we have shown psi is 1, 1. So here psi is what? 1, 1. Okay, so we got psi is 1, 1. Now we have to show that psi is on 2. Okay, so we have to show that psi is on 2. So you take an element in U. Okay, so I have to take an element in U. So I take small u in U. Since f is on 2, since f is on 2, there exists an element v in V. Since f is on 2, I can find an element v in V such that f of v is equal to u. Okay, f of v is u. Now what is f of v? F of v is nothing but psi v plus k, which is equal to f of v, which is equal to u. So I took one element in u. I find that its image is in v plus k. Okay, where v plus k belongs to v by k. So therefore psi is on 2. Okay, so psi is 1, 1 on 2 and a vector space homomorphism. Therefore these two vector space should be isomorphic to each other. So we have here V by K is isomorphic to U. Thank you.